beautiful people. So let's solve this problem. Uh, we are given the wedge product of two circles, and we are asked to determine the number of two sheeted coverings of this space up to isomorphism of coverings. So let's proceed with the solution. We have these three sentences that are logically equivalent when x is connected by path, locally connected by paths, and semi-locally simply connected, right? All of these definitions you can find in Alan Hatcher book on algebraic topology in the covering spaces chapter or section. So we have these three affirmations that are logically equivalent, and let's see what they mean, each one. The first one is pretty simple. We have that two coverings are isomorphic via isomorphism of coverings. The second one says that there exists a bijection between the fibers of some base point on x that we are naming x sub 0 that preserves the action of the fundamental group of x in that point. Let's clarify what the second one means. This means this. Suppose we are going to make an example of this to illustrate what it is saying. So we have our space that we are dealing with and a covering space of this, right? So let's draw some covering space. Let's say this and this, and we are going to make this one, this, and what is the no, I am drawing it horrible, right? And this one, right? Like this. This is our covering. Oh no. Let me draw it in the right way. See? And like this. Right? So this is our covering. Okay, so let's clarify what the action does on the fibers, right? Suppose we have this loop that we are naming V, that what it does is it goes like this, right? So this loop determines a multiply class that is an element of the fundamental group. So let's see how that class acts on the fibers. We are going to use this algorithm for determining what the action of some element of the fundamental group does in a fiber, right? So if we have a thing on the fiber, let's say this thing, this blue thing, the algorithm of what the loop does on that thing is the following. We consider not the loop, but the loop traversed in reverse, right? So the loop is going like this, no? The loop is going like this, right? In reverse, okay? And we consider the unique lift of that loop that starts in the point in which we are interested in the action, right? So which one is the lift of that loop that starts on the blue point? Well, it needs to be this one, like this, no? This is the loop, and the action on the blue point of this is the endpoint of that lift. That is the blue point goes to the red point via the action of the loop, right? So that is the recipe. And what does it mean that H preserves the action? Well, it means that, like for instance, if we call gamma this loop, this means that uh, H on gamma of some thing in the fiber of x sub 0, needs to be gamma acting on H of x of the same thing. Obviously, this action depends on the covering space, right? So here, gamma acting on x, we are meaning that the action that p sub 1 induces on the fibers. And if we have, like in this sentence, another covering p sub 2, let's say we have another thing over here, then the action over here is the one induced by p sub 2, right? So this means that H preserves the action of the fundamental group, right? Okay, let's move on. Now, what does the third one means? Well, the description that we already did is this action and this other action. Rho sub 1 is the action associated with P1 covering, and rho sub 2 is the action associated with P2 covering. So what does it mean of that these two actions are conjugate? Are conjugate via S sub 2. That is, well, via the cardinal of the fiber. That in our case is 2, right? What does this mean? Well, if we name the things on the fiber 1 and 2, and in the other fiber equally 1 and 2, what this does means that rho 1 is conjugate to rho 2. Well, it means this equation. It means that there exists a permutation in two elements that makes this equation hold. But what does this equation means? It means that for any gamma on the fundamental group, and any symbol in the 1, 2 set, the following equation holds. H on J, it is a symbol, and so it makes sense to act via gamma and the covering space 1 on this symbol, like we already described it earlier, and we get this another symbol. This is another symbol of the 1, 2 set, and finally we can act via H inverse on this symbol, right? So this needs to be the same as the action via the second covering on the J symbol, right? So this means that those actions are conjugate via an element of the S2 group. Okay. Well, this theorem Hatcher doesn't put this as a theorem. He only mentions it in page 69 to 70. In that pages there are the construction of these three sentences. Okay, so let's see how do we use those for solving our problem, right? Okay, well, we need using tree, we are going to estimate the number of coverings that we are asked for. Okay, so we need to determine first how many actions of the type that is uh, underlined in blue there exist, right? But an action of this type, it only means that it is an homomorphism of this kind, no? Between the group, the fundamental group of the wedge product of circles that we know that is this free product and S2, right? So we need first to determine this cardinality, okay? Well, by the characteristic thing of the free group, this we can biject with the pairs of morphism between the integers, the additive group of integers and S2, right? So this. Okay. Now, since the integers, the additive group of integers, it is generated by one generator, that we are going to distinguish between the left factor and the right factor. Let's say this one is this, and this one is generated by this, right? We only have to determine how the morphism F and G act on the generator. So it has only two choices, right? If A or B is the generator, and we have one of this type of morphism, we have only two choices, right? To get the identity element of S2 and to get the other element of S2, that is a transposition of the symbols, right? This one doesn't makes nothing to the symbols, and this one interchanges the symbols, right? Okay, so it only has that two choices, right? So by analogous argument, we have that G has only two options like that. So the cardinality on the right is 4. Okay? So at most, we have four, four actions of the fundamental group on the S2 group, right? So we need to determine the conjugacy class of each one of that action via an element of the S2 group, right? By doing the calculations, we have that the this set over here is we can represent via the, well, we have the trivial morphism and the one induced by the pair TE and the other by the ET pair, and lastly the one of the TT pair, the transposition. So we have this morphism represented by this, right? Well, the trivial is the EE, the one induced by the EE pair, okay? So uh, now we only have to calculate the conjugacy classes via elements of S2 of each one of these morphisms, right? So let's, for instance, calculate the conjugacy class of this. Well, firstly, we note that S2 has only two elements, the E and the transposition. So if we conjugate by the E, we get the same. So we only have to conjugate the morphism via T. Now, T is its own inverse, so this T inverse is just T, right? Okay, let's see what this morphism is, right? So let's see how this acts on a J symbol. By definition, this means that we transpose G, and what do we do? Um, so let's verify that what? See. Mhm. So we need to see how this acts, since, okay, let's see. This is another morphism, right? Of this type. So in order to determine how this acts, we need to determine how it acts on the generators of the integers of the product of the free product of integers. So let's see how this acts on A generator and a J symbol. By definition, this is transpose J, sorry, and this morphism on A, and finally transpose that. Okay. Well, this morphism EE on A, it is just the identity. So this part over here, it is just the what? The identity on S2. So we get this. Transpose and then do nothing and then again transpose, right? So this is just the identity on G, right? Okay, so this morphism that we're dealing with, it is just the identity, right? Well, by making the same computation but in the B generator, what we get, it is to transpose first. Sorry, we need to evaluate on a J symbol. transpose the J symbol, then evaluate this on V, and finally transpose. Well, this is again the trivial element of S2. So again we get that this is J. So this conjugation of this morphism, it is just the same, right? It is the identity. So its conjugacy class, it is itself, right? Well, if we do this analog procedure in this one and this one and this one, we will get that each one is its own conjugacy class via S2, right? So we have this type of equation. Its conjugacy class via S2, it is just the same, right? This holds for the four of these elements. So we have four conjugacy classes for uh, via elements of S2, right? So what are we getting? That there exist four, two sheeted coverings of this space up to isomorphism, right? So a good exercise is to draw them, right? So we're going to do that. The first one, it is very simple, right? It is this one, this projection, okay? There's nothing to do here. And the second one, it is a little more complicated, and we have already seen it earlier in the video, right? How it is this? Well, we get this one that goes like this when this goes like this, so that is our homomorphism, and the other one goes like this, up, and enters here, right? And this one goes like this, down, right, and a turn, and we get over here, right? And last one goes just like this, right? This is the second covering of our spaces, our space. The third one covering, it is similar to this one, but note that the tricky part, the tricky part occurs in the left side, right? If we call this A and B, right? So we are going to do that horrible thing now in the B side, okay? So our third covering goes something like this. Here it goes very easy in the A side, and in the B side we do the analog of that thing, right? We go first from down to up like this, and we go lastly like this. Something like that, right? So this is our third covering. Well, you may ask if these two coverings are not isomorphically these two coverings, because they look a lot like they are the same, right? And well, let's see the fourth covering. The fourth covering is a little more trickier. It goes like this. We go first up from this to this. We go over here, right? Now we go from here down like this, right? And lastly, we go from here down to here, and from here we go up like this, right? So this is our third covering, right? Our fourth covering. Okay, so 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 what it only remains to prove that the ones that are pointed to each other with the blue arrows are not isomorphically, are not the same, right? But for that we use the second part of the affirmations, right? We are going to see that there are no bijections that preserve the action of the fundamental group. So we are going to consider, well, the only two bijections that we have. Let's number the vertex. 1 and 2. 1 and 2, right? So the only bijections that we have are h1 that sends 1 to 1 and h2 that sends 1 to 2, right? So let's see that the first one does not preserve the action. I'm going to erase this discovery. Okay, the first one does not preserve the action. For that, we are going to use the B loop. That is this one, right? This determines an element of the fundamental group, right? Okay, so we need to see that H1, well, that first V acting on 1, is it the same as H1 on 1 and V acting on that thing, okay? So let's see. Let's first determine how does V affects 1. Do you remember it is lift the reverse of V, uh, the one which starts on 1, right? So which loop it is? Well, this is the reverse of V, right? So this is this loop, right? So which is the lift that we are going to use? Well, let's see. It needs to be this one, right? This one. From down to up, okay? Oh no, I have made a mistake because this does not start in 1. So which one is going to be? It needs to be this one, right? This one that goes like this, from up to down, right? So V acting on 1, it is what? It is 2. It is the end of that loop, of that green loop, right? So this is 2. H1 on 2, what is this? H1 on 2 by definition, it is the identity, so this is 2, right? This left side is 2. Now let's see the right side. H1 on 1, it is by definition just what? 1, right? So we need to determine how does V act on 1, right? So again, we consider this loop, well, V in reverse, right? So this loop, and we lift it to the one loop, the one path that starts in 1, right? So which one starts in 1 and lifts this loop, this purple loop. It needs to be what? Like this one, right? This one, okay? So V acting on one, on the second, on the left, on the right covering, it is just one. It is the same, right? So this is one, and 2 doesn't equals 1, right? So this bijection between the fibers it is not good for preserving the covering structure. Okay, this one does not preserve the covering structure, right? Let's see the other one. We use V again, so we need to see that V acting on one and then send it via H2. Does it is the same as H2 on one and V acting on that, right? So let's see, again, we have that V1, V acting on 1, it is what? It is 2. The last time in the last 30 seconds we did that, right? So yes, this is 2. H2 on 2, it is 1, okay? And the other side, what does it say? V acting H2 on 1, it is just V acting on 2, okay? So let's see what does V does in 2. We have again the V in reverse, and we need to lift it on 2. But the lift is just this one, no? Goes like this, right? So V acting on 2, it is just 2, right? And 1 does not equals 2. So these two coverings spaces cannot be isomorphic, and this surprised me very in very great detail, because it seems like the two spaces are homeomorphic, and the homeomorphism, it is very simple. It is just like a reflection or something like that, but it cannot be made into a isomorphism. So there are isomorphism. So the isomorphism needs to preserve additional structure than the topological one, and this is a very good example, and I loved this exercise.